Welcome, everyone. I'm excited to have you here today. We're going to explore belt filter press technology, an advanced solution for dewatering in municipal wastewater treatment facilities. In this presentation, I'll walk you through how these systems work, their benefits, and why they're essential for modern wastewater management. So, let's get started and discover how this technology can make a difference. So, you might be wondering, what exactly is a belt filter press? Well, it's a mechanical system designed to dewater wastewater residuals, turning liquid waste into a solid, non-liquid material known as cake. The process involves placing biosolids between two tensioned, porous belts that pass over a series of rollers. As these belts move over rollers of decreasing size, increasing pressure is applied, which squeezes out the water. All belt filter press designs share 4 key zones. First, there's the polymer conditioning zone, where chemicals are added to prepare the biosolids for dewatering. Next is the gravity drainage zone, where any free water naturally drains away. Then, there's the low-pressure squeezing zone, which helps form a firm, manageable cake. Finally, we have the high-pressure zones, where rollers of smaller diameter exert maximum force to extract as much water as possible. Advanced designs often feature larger filtration areas, additional rollers, and even variable belt speeds. These enhancements can boost the solid's content in the cake by about 5%, making the process more efficient. Now, the consistency of the dewatered cake can vary quite a bit, from a custard-like texture to something more like moist soil, depending on the specific processing parameters and the characteristics of the biosolids we're working with. Let's also quickly touch on the key components that make this system work: the dewatering belts, rollers and bearings, belt tracking system, tensioning system, controls and drives, and the belt washing system. Each of these plays a vital role in ensuring reliable, efficient operation. So, in essence, the belt filter press is a sophisticated but effective way to reduce wastewater volume and prepare residuals for disposal or further treatment, fitting perfectly into our overall goal of sustainable water management. Let's talk about why dewatering biosolids is so important. First, reducing volume helps lower both storage and transportation costs by removing excess water. This makes handling much more efficient and cost-effective. Second, it ensures landfill compliance by eliminating free liquids before disposal, which is often a regulatory requirement. Third, dewatering improves fuel efficiency because drier biosolids require less fuel during incineration or thermal drying processes. Fourth, it prepares the biosolids for composting by creating a material with enough void space and volatile solids, which are essential for effective composting. Fifth, dewatering helps prevent runoff by avoiding pooling of biosolids during land application, reducing environmental impact. And finally, it optimizes the entire process by enhancing subsequent steps like thermal drying, making the whole operation more efficient and sustainable. Overall, dewatering plays a crucial role in managing biosolids safely, economically, and in an environmentally responsible way. When considering when to use belt filter presses, it's important to remember that they are a common and versatile type of mechanical dewatering equipment. They work well for most biosolids generated at municipal wastewater treatment plants. However, their cost-effectiveness really depends on factors like the size of the facility and specific operational considerations. Now, if we look at facility size, mechanical dewatering methods such as belt filter presses might not always be the most economical choice for smaller plants. Say, those operating at less than 4 million gallons per day. For these smaller facilities, it's worth evaluating whether hauling liquid biosolids to application sites or paying other processing facilities to handle dewatering might be more cost-effective. It's also useful to consider alternative dewatering methods for smaller operations. Techniques like drying beds or reed beds often have lower capital and operating costs, especially when dealing with reduced biosolids volumes. These options can sometimes be more suitable and economical depending on the specific circumstances. Finally, selecting the right equipment really should be part of a broader, site-specific biosolids management plan. This plan should identify all potential processing and end-use options and it should include detailed cost estimates for each viable approach. Making an informed decision means looking at the overall picture, costs, facility size, operational considerations, and long-term management goals to choose the most effective dewatering method for your facility. Let's take a closer look at some of the key advantages of belt filter presses. First, they require low staffing requirements. This is especially beneficial if your equipment is large enough to handle all solids in just one shift, because it helps minimize labor costs and simplifies scheduling. Next, maintenance is quite straightforward. In most cases, plant maintenance crews can handle the routine upkeep, with belt replacement being the primary expense. The good news is that belt replacement procedures are generally simple and easy to perform. Another important benefit is quick startup. Unlike centrifuges, which can take up to an hour to reach operational speed, belt filter presses can be started and shut down rapidly. This flexibility can really improve your operational efficiency and responsiveness. And finally, belt filter presses operate much quieter than centrifuges. This creates a better working environment for operators and also helps reduce noise pollution concerns around your facility. All these advantages tie into our overall theme of efficiency and operational simplicity, making belt filter presses a smart choice for many applications. Let's talk about some of the operational challenges we might face. First up is odor management. Odors can definitely be problematic, but the good news is they are controllable. Using good ventilation systems is key, and chemicals like potassium permanganate can help neutralize odor-causing compounds. Some manufacturers also offer fully enclosed equipment, which can really help minimize odors and vapors in the operating room air, making the environment more comfortable and safer. Next, we have feed variability. Belt presses are quite sensitive to changes in feed solids concentration or organic matter. When the feed varies, they require more operator attention to keep everything running smoothly. However, this issue can be mitigated if the feed comes from well-mixed digesters, which provide a more consistent feed characteristic, helping to maintain stable operation. Then, there's the issue of oil and grease. Wastewater solids with high oil and grease content can cause problems like blinding the belt filter. This reduces the solid's content in the cake and can hamper overall performance. In such cases, pre-treatment of the wastewater may be necessary to remove or reduce the grease before feeding it into the belt press. Feed preparation is another important point. To prevent damage to the costly belt material, solids need to be screened or ground to eliminate sharp objects. This extra processing step adds an important layer of safety and helps prolong equipment life. Finally, let's discuss belt washing requirements. Cleaning the belts at the end of each shift, or more frequently, can be quite time-consuming and water-intensive. To address this, automatic belt washing systems are a great option, and using plant effluent for washing can significantly reduce water and labor costs, helping us operate more efficiently. All these operational challenges highlight the importance of careful planning and proper equipment choices to ensure smooth, efficient, and safe operations. When we talk about design and sizing considerations for belt presses, it's important to remember that sizing isn't based on wastewater flow itself, but rather on the weight or volume of solids that need to be dewatered. This means we need a thorough understanding of the current solids production and also anticipate future changes. Critical factors include the daily amount of primary solids flowing through the plant, as well as waste-activated or trickling filter solids produced each day. We also need to consider the volume of thickened solids that will require dewatering daily, and the range of dry solids concentration in the feed to the belt press. Don't forget to factor in potential increases in solids production over time, and any changes in sewer operations that could affect solids quality or organic content. All of this information is essential to develop an effective biosolids management plan, which should guide us in selecting the right equipment and ensuring it fits our needs now and in the future. When planning capacity, always design for some excess capacity. This way, you can handle the anticipated solids during regular operation without any issues, even if a unit goes offline. If you only need one unit, consider having an alternative plan to remove solids in liquid form to avoid bottlenecks. Now, regarding zone specifications, polymer conditioning typically involves about 265 to 379 liters, or roughly 70 to 100 gallons, of polymer, placed about 0.6 to 1.8 meters from the press. For gravity drainage, the goal is to achieve a 5 to 10% increase in solids concentration, helping us optimize the dewatering process efficiently. Let's take a closer look at how performance varies depending on the type of sludge being processed. As you can see in the table, different sludge types have quite a range of characteristics that influence how well the dewatering process works on high-pressure belt filter presses. For example, raw primary sludge typically contains between 3 and 10% solids, and it requires about 1 to 5 grams of polymer per kilogram of sludge. The resulting cake solids can range from 28 to 44%, which is quite good. In contrast, raw waste-activated sludge, or WAS, tends to have a much lower solids content, only about 0.5 to 4%, so it often needs more polymer, around 1 to 10 grams per kilogram, to achieve effective dewatering. The cake solids here are usually between 20 and 35%, which is a bit lower than primary sludge. When we look at combined primary sludge and WAS, the performance characteristics are somewhat intermediate, but the variability remains high. Similarly, anaerobically digested sludge types tend to have different ranges, often with slightly higher or lower solids content, depending on the process. For instance, anaerobically digested primary sludge still has a solids range of 3 to 10%, but the cake solids can be slightly higher, up to 36%. Meanwhile, anaerobically digested WAS has lower solids, around 3 to 4%, but may require more polymer, especially in the 2 to 10 grams per kilogram range. It's important to note that thermally conditioned primary sludge plus WAS can reach cake solids of up to 50%, which indicates the significant impact of thermal conditioning on improving dewatability. Overall, the key takeaway is that the performance of dewatering processes is heavily influenced by the specific type of sludge we're dealing with. Understanding these variations helps us optimize polymer dosing and operational parameters to achieve the best results. Connecting this to our overall theme, tailoring our approach based on sludge type is crucial for efficient and cost-effective wastewater treatment. Let's now look at the operations, maintenance, and costs involved in running a belt press system. Starting with daily operations, operators are responsible for mixing the polymer, dosing it correctly, and monitoring the usage throughout the day. They also need to observe the feed and the resulting cake multiple times a day, making necessary adjustments to keep everything running smoothly. Additionally, rollers and bearings require frequent lubrication to prevent wear and ensure optimal performance. Key records to keep include the volume of biosolids fed into the system, the amount of polymer used, and other chemical consumptions. In terms of labor, a single belt press generally needs about 4 to 8 staff hours per day, which includes lab testing. For larger setups with 6 to 8 presses running simultaneously, the total labor might be around 8 to 10 hours daily. Interestingly, larger plants tend to use less effort per belt press, and if you move to highly automated systems, the labor drops further, although you'll need instrumentation specialists to manage the automation. Now, on to maintenance. The belts should be cleaned daily using high-pressure wash water after the cake has been removed. Belt replacement is the most common maintenance task, with an average belt lifespan of around 2,700 hours, though this can range from as little as 400 to as many as 12,000 hours. These belts are designed for easy replacement, minimizing downtime when they need to be changed. Regarding capital costs, the price varies depending on the size. A 0.5 meter belt costs around $47,500 and can handle about 500 dry pounds per hour. A larger 1.5 meter belt costs approximately $115,000, with a capacity of roughly 1,625 dry pounds per hour. Keep in mind, these figures are based on a 5% solids feed, and do not include installation, shipping, or additional equipment. Operating costs typically fall between $80 and $200 per dry ton of solids processed. Polymer conditioning can be a significant part of these costs, ranging from about $2.65 to over $91 per million gallons, with an average around $24.38. For example, raw primary sludge might cost about $12 per dry ton, whereas more difficult residuals could go up to $80 per dry ton. Permanganate adds roughly another $1 per million gallons. Finally, a few additional notes on system enhancements. Adding automation can increase capital costs by around 5%, but it significantly reduces labor requirements. Also, advanced designs can boost the solids content in the cake, which can improve dewatering efficiency and overall process performance. All these factors are essential to consider when evaluating the overall feasibility and efficiency of your biosolids management system. Now, let's take a closer look at odor control and the advanced features that can really improve system performance. First, we have self-enclosed systems. These are designed to minimize the release of foul air that requires treatment. They use induced draft fans to create a slight negative pressure, usually around 100 CFM per meter of belt width, which helps contain odors. When designing these systems, it's important to minimize gaps and enclosure volume, place maintenance components outside the enclosure, and include automation for easier operation. Using stainless steel and providing multiple access hatches makes maintenance simpler, and designing for easy belt removal ensures minimal downtime. Moving on to chemical odor control, we often use oxidizing agents like potassium permanganate. These help reduce odors from sulfides, lower the need for polymers, and increase cake solids content. To keep emissions low, it's best to minimize liquid storage, keeping it under 24 hours before pressing, to prevent pH drops and organic sulfide emissions, which can be problematic. Next, let's discuss polymer optimization. It's crucial to have feed points at multiple locations, giving flexibility in how we introduce polymers. Gentle mixing is key to avoiding flock shearing, which can compromise treatment efficiency. Properly sizing dilution and aging systems ensures consistent polymer performance. Also, selecting polymers that are stable at higher temperatures and pH levels is especially important when dealing with lime stabilization or high-temperature processes. And for those interested in further details, additional fact sheets are available online at the EPA website. Connecting all these features back to our overall theme, effective odor control and system efficiency, these advanced features help us design safer, more reliable, and environmentally friendly treatment systems.